Our first question, we've got a planet in orbit around a star. So start off by drawing a diagram. And we're asked to, using Newton's law of gravitation and the expression for centripetal acceleration, show the orbital period is related to r by t squared equals kr cubed. So we're aiming for something in this form. And then we can generalize the force centripetal is equal to, and that's the mass of the planet. And we're also using Newton's law of gravitation. And that's the force of gravity is equal to So because the planet is in a circular orbit, it's not getting closer or further away, we'll say that the forces balance. So, whoops. We'll cancel out the m's and we'll cancel out one of the 1 over r's. And now we have this term v that we want to change. So what can we substitute v for? So the speed of planet M is around this circle. I don't know which way it goes. I'm going to go this way. And that's distance over time. So speed equals distance, which is 2 pi r. That's the circumference, and the orbital period. We'll call that t, because we know we need to get t in our starting equation up here. So let's substitute that in. Let's go v squared equals 4 pi squared r squared over t squared, and put that in here. So now we have g m of r and I'll rearrange this. So we have our final answer. Oops, I've lost my squared sign for the pi. So k is a constant, but it's not a universal constant. So it is made out of values that don't change, but this is k for Earth's or the planet's orbit around the star of mass m. So it's for this situation. If at some point we had to look at a different orbit, say a satellite around this planet, k would be different for this situation. It would also be constant, but it's a different constant. The second part of this question, we're asked to find k for Earth's orbit. So we want to find t is 1 year, is 3, 6. Times hours, minutes, seconds. So that's the value of t in seconds. And we're given r is equal to 1.5 times 10 to the 11 meters. So we substitute these values into t squared equals k r cubed. I'd rearrange that first because we want to find k, and just put both of those values in. The final part of this question, we have a geostationary satellite in a circular orbit above the Earth's equator. So I'll refer back to this sheet because those constants we derived will be useful. But I'm going to start off by drawing a diagram. So here we have the planet, which has mass m, and we've got a satellite there. And we want to find out that orbit radius. I'll call it little r. So what we know is that this is geostationary. So its time period is the same as that of Earth, which is 24 hours. So 24 times 60. So we also know the relationship t squared equals k r cubed. Oops, sorry, bad writing there. But k here, that is k for the Earth and satellite. So we're going to need to have a look at our equation for k again and slightly revise that compared to, we can't just use the numerical answer from part 2. So k is 4 pi squared over gm. And in our previous example, we were looking at this situation where we had the planet, the sun and the planet. So this is the like center point. So that means that our k would change for this situation here into 4 pi squared over gm, and that m is the mass of the planet now. And because we know it's Earth, we'll use the mass of the Earth symbol. So I'm going to substitute those back together. And we want to find the radius, so let's rearrange first. So r cubed is equal to t squared over k, and then put k in. Oh, I should have been using little r through there, but we'll call it r satellite. you know this value of mass of Earth